All right, good day to y'all. Welcome to another quantum field theory core seminar. We're delighted to have Professor Fiona Burnell with us, who is currently a professor at University of Minnesota. After earning her PhD at Princeton University under the supervision of Professor Robert Mang, he went to also college for postdoc before joining University of Minnesota. Her research largely lies on exotic phase matter, and she cared about topics like topological insulators and deal with models that's like in condensed matter theory. During the seminar, if you have any questions, please use the raise hand button on Zoom. I will then grant you speaking permissions. Your active participation is very, very appreciated. Now we'll pass the conference to Professor Fiona Burnell. Thank you for accepting our invitation.
Okay, well, yeah, thanks for being here. And I want to echo the encouragement to ask questions. It's a lot more fun when I hear from you guys in the middle of a lecture. I should say my PhD advisor, I did work for Robert Mann as an undergrad, but my PhD advisor was actually Shivaji Sandhi. So just as it's being recorded, I should put that on the record. Yeah, so I'm going to tell you today a little bit about quantum field theory in condensed matter physics. And so to start by just sort of talking about, what is condensed matter physics? Like, what kinds of questions are we interested in? And I think there's two ways to frame this. So I think the first thing that a lot of people think of when they hear condensed matter physics is, oh, you're trying to understand materials. And that's true at some level. What one goal of the field is we want to study materials or fluids, often in a regime where quantum mechanics is important. And basically with the kind of practical goal of understanding what they can do, what they're good for, and how they might be useful for developing new technologies. And so, ultimately the fundamental science that's done in condensed matter physics and in material science, percolates down to technologies that change all of our lives. And, this has been true throughout human history. Everything from, when people first learned to smelt metals, and that brought us out of the Stone Age, to the transistor, which brought about the sort of computing revolution. And nowadays people are thinking a lot about materials to do quantum computation. So there's this very kind of practical side of it. But I think as a theoretical physicist, the reason that I find it interesting is that, at base, what we do is we study quantum mechanical systems where there's many particles and they're all interacting. And, quantum mechanics is important. Okay. And, these systems are incredibly complex at a microscopic level. There's no way you can calculate anything kind of from the ground up because they're just too complicated. But I think because they're so complex, they can realize a really rich variety of behaviors. And so, there's a practical payoff to understanding them, but also theoretically, I think condensed matter systems have taught us a lot about quantum field theory as well, and what physics can sort of do for us. Okay, so so let me start by, kind of giving you a very basic picture of what kinds of questions you might want to answer if you actually have a material and you want to understand whether it's going to be useful for some application. And, so basically the kinds of questions that we ultimately would like to answer are ones that we can, essentially test experimentally. So for example, a very important question is, does this material conduct anything? Does it conduct electric charge? Does it do that well or badly? Does it conduct, can it actually conduct spin? So transport, kind of magnetic dipoles. Does it do that well or badly? Does it conduct heat? And so on. Okay. And so these are, basically questions about 2-point functions of, the particles that carry charge, spin, heat, and so on in your material. So understanding how to describe this system, with a quantum field theory and calculate, 2-point functions, or more generally response functions, is one of the primary, things that we're interested in doing. Okay. A second, kind of experimental probe that's very common is, you take your sample and you scatter stuff off of it. Maybe it's light, maybe it's, X-rays, maybe it's neutrons, so little particles. And, when you do this scattering, you can resolve something about the structure of the material. Okay. And then, so that's another kind of question that we like to be able to answer. And more recently, a question that people are very interested in is, can I use a material like this to store quantum information in a way that's sort of robust to noise? So a priori, I'm going to say very much about this in the rest of the talk, but if you're interested, you can ask me maybe in the break, because this is a kind of a big one. Okay. But yeah, basically a lot of the kinds of calculations that we want to do can be framed as, let's describe this quantum many-body system using some kind of field theory. And we have to figure out what kind of field theory we should write down. And let's calculate correlation functions of that field theory. And that's basically because these correlation functions describe things that can be measured. Okay, good. Now, like I said, and I'll kind of click back here, when we're studying materials, we're talking about kind of moles worth of atoms all in some complicated lattice, and each atom has a whole bunch of electrons, and basically all of those nuclei and electrons and all and so on are interacting with each other. And so this is an incredibly complex microscopic system. And so you might wonder, how is it that we can make any progress whatsoever in understanding this? And so a really crucial observation is one that I think is probably familiar to many of you from, high school chemistry or whatever, which is that most materials, if you kind of zoom out a little bit, they have wide regimes of parameter space where they kind of do the same thing. Okay, so this is just an example, but this is the phase diagram of water, right? And, the key observation is that as a function of pressure on the y-axis and temperature on the x-axis, okay, there's really, kind of only 3 qualitatively different regimes. And this is very important when you live in a place like Minnesota, okay, that, when the temperature is low enough or the pressure is high enough, okay, that, water is solid and you can go to the lake and you can walk on it. So we do that a lot in the wintertime. On the other hand, in the summertime, when it gets warmer, right, you cannot go to the lake and walk, you go to the lake and swim, okay? And, from the point of view of your experience interacting with the water, it doesn't make that big a difference whether you're at a temperature of, 5 degrees below zero or 20 degrees below zero. Because basically what you experience is this water is now solid, it's ice, and I can walk on it. And similarly, from the point of view of your experience with the liquid, it doesn't matter too much whether your water is at, 10 degrees Celsius or 50 degrees Celsius, you can still sort of drink it or whatever. Okay. And so when we go about trying to understand these systems, we don't have to sort of microscopically describe every single one of these possible conditions in this sort of this two-dimensional grid. All we need to have is really sort of one example. We need to be able to understand one point in this solid phase diagram and one point, sort of in this liquid phase diagram. Okay. And so these are pictures just to sort of illustrate. Now, this is a simplified phase diagram of water. It turns out that, depending on pressure and so on, solid ice actually has some different configurations, and that's why you get all of these super cool snowflakes. But, to a rough approximation, you have a different phase, and within each phase, things more or less look the same when you zoom out kind of at long distances, which is where we're interested in for applications. Okay. Now, and actually, here's where I should ask, have you guys talked at all about sort of loop diagrams and flowing coupling constants at this point in your course?
Nope, not yet.
Not yet. Okay.
Next week.
Okay. All right. Well, great. So I will, sort of say these words, and as you see loop diagrams and coupling constants and ultimately something called the flow of coupling constants, this will make more sense. But basically, there's, you could imagine that as, there's sort of one field theory, as you look at the system on longer and longer longer and longer length scales, there's kind of one field theory that, that everywhere in this solid region sort of flows to, that sort of basically describes the long distance properties of this solid. Okay. And there's a word for that field theory, you call it a renormalization group fixed point, and that the renormalization group, it's not a group, but it just means that kind of as you zoom out and zoom out and zoom out in this field theory, there are some effective coupling constants, and that they change. And, kind of as the length scale gets very, very long, eventually they stop changing. And you have kind of this paradigmatic field theory describing the solid. And same thing for the liquid. Okay. And so we can understand a lot of different solid state systems by thinking about only a small number of kind of long distance field theories. Okay. All right. Okay, good. And so, how does quantum field theory enter into this understanding of phases of matter? Well, the first thing is that typically, for most phases of matter, we can write down a quantum field theory that describes these long distance properties. Often, right? And so in particular, we can use that field theory to calculate different responses, okay, conductivities and so on, that we could actually measure in an experiment. And one feature of these field theories is that in most situations, not all situations, but in most situations, microscopically, when we're thinking about a solid, for example, right? So not a liquid, but if you're thinking about a solid, you have some kind of crystal lattice. But often that crystal lattice structure is relatively unimportant at long distances. And so these field theories would look fairly familiar, many of them that we use to describe these systems. If you've looked at, things like phi to the fourth action for a boson, that's one that describes, for example, a lot of magnetic materials. Okay. And so that's one thing that's useful is, if you sort of know what your phase is and you can deduce what the effective field theory should be, you can then use that to calculate experimental responses. The other thing that we do with quantum field theory is we determine, we can use quantum field theory to say, well, my material looks like this at high temperature. Okay, this is usually done for metals. So maybe we have something that's a metal at high temperature. As we cool it down, what's going to happen to it? Okay. And so we can use quantum field theory to look at sort of instabilities towards certain kind of phases as the temperature goes down. And another sort of really big application, and I won't have time to talk about this today, but it's a very beautiful one, is understanding the physics of second order phase transitions. Okay, so there's basically a lot of interesting quantum field theories that describe points where you're going between two different phases in a phase diagram. Okay, the phase diagram of water, not so much, but there are many examples where we have these beautiful subjective conformal field theory, where really the system forgets about all the microscopic details and comes up with these interesting interacting field theories that we can realize and test in the lab. Okay. So these are the kinds of things that, they're a sample of the kinds of things that we do with quantum field theory and condensed matter. At the same time, I think, one of the things that I really like about condensed matter is that I also think that condensed matter is a useful tool, in a sense, for studying quantum field theory. Okay. And there's a few reasons for this. So the first thing is that many of the classic sort of phenomena, and I'll give a few examples in the next slides, that people, that you will learn about in a, sort of a 2-semester quantum field theory course, many of them are realized in solid state sort of material systems. And the reason that that's, a great thing is because solid state experiments, it's not that they're easy and it's not that they're cheap, but relative to particle accelerators or relative to trying to get cosmological data, they actually are. These are sort of labs that can exist in a given building. people can make these materials, people can do the measurements. It doesn't take 25 years and, you know, however many $1 billion. And so I think it's really, you know, a nice thing to have these experimental probes of the quantum field theories that, you know, maybe people originally thought about sometimes in the context of high energy or particle physics. Okay, so that's one thing that condensed matter can kind of teach us about quantum field theory. A second thing, and I think this has been happening quite a bit in the last sort of 10 to 20 years, is that are these last two. So first of all, that solid state systems basically are very diverse, right? They're very complex. There's many interactions, and that means that really we can make a lot of different kinds of materials. We have knobs to tune, so we can apply external fields. We can, you know, make kind of sandwiches of different materials. And so basically we can realize a really wide array of very different kinds of material systems. Okay. On the other hand, there's only one universe. Okay. So, you know, if you want to sort of use particle physics to think about, you know, as kind of a inspiration for what kinds of field theories you should think about, well, that's a little bit more limited. And so I will tell you about some nice examples of quantum field theories that are not known to be, you know, relevant, say, to high energy particle physics, but that are certainly relevant to understanding solid state systems in the lab. And the other thing is that, you know, there are some kinds of quantum field theories that have been well motivated to study in the condensed matter setting. And I will give one example, although I think towards the end of the talk, where, you know, these questions are sort of not natural at all in a high energy, in the context of thinking about high energy physics. And so thinking about condensed matter systems and using quantum field theory as a tool to understand condensed matter systems can also motivate us to ask new kinds of questions about quantum field theory. Okay, so this is kind of my, broad overview. I'm going to give you a few examples just briefly of, you know, some kinds of things that we see in solid state systems, and then I'll kind of hone in on one particular example that I'll spend some more time on. Are there any questions at this point about the general picture? Kind of what we're doing and why? No.
I think it was very clear.
Okay, all right. All right, so I wanted to start by, and as I said, you know, I have a few examples that I'll go through relatively briefly, just kind of to sketch. But I wanted to start by, you know, giving you guys a few examples of phenomena that, you know, that you might learn about in field theory that are realized in solid state systems. Okay, so the first one is what we call spontaneous symmetry breaking. And so let me first explain what that means in the context of thinking about phases of matter. So we can come back to this phase diagram of, you know, water, okay? And we can ask, what is different between liquid water and solid ice, right? You know, kind of how do we sort of at the most abstract level understand why these two phases are not the same, okay? And one way to think about that is that in the regime where water is liquid, if you kind of zoomed in and asked, what are those molecules doing? Well, of course, you know, the water molecule is very polar, and so there's strong short-range correlations between these molecules. But basically, if you look at this kind of schematic of liquid water, it looks kind of like a jumble, and it actually is basically a jumble. And what that means is that, you know, knowing that I have, you know, sort of like a water molecule. Oh yeah, you guys can't see my mouse. Okay, so a water molecule, you know, sort of over here, oriented in this way, doesn't allow me to predict anything about the locations or orientations of the water molecules far away. So it certainly does allow me to predict something about their locations and orientations close by. But as you go farther away, that information, you know, is sort of less and less useful. And very quickly, you know, I find that there is no correlation between the positions and orientations of these water molecules. Okay. For ice, on the other hand, the story is very different, right? So you can see this is a picture of ice. Ice is a solid, and that means that these molecules are arranged in a regular ordered fashion and a crystal lattice. Okay, now this is sort of a perfect ice crystal. And of course, you know, the ice that, well, you guys probably don't see ice in the wintertime, but the ice that we see like on the sidewalk here in the wintertime has lots and lots of, you know, sort of crystal defects, but you know, there's sort of little bits of it that look like this. Okay, and so what's different about this is that you can see that there's sort of a regular order here. So in particular, if you look here and you say, well, this water molecule is sitting here in this orientation, that allows you to predict the position of other water molecules that are quite far away. This guy over here, and I could extend this picture out very far. And, you know, basically in the limit that this is a perfect crystal, this gives me, you know, a very high predictive power of the location of the water molecules as I get very far away. Okay. And okay, fine. So, you know, this has some predictive power in terms of there's strong correlations between the positions here and the orientations and not here. So the simple way to say that is that in the crystal, okay, you can see that if I took this bit of liquid water, and I kind of took the picture and turned it around or whatever, you wouldn't really be able to tell. Whereas if I took this crystal, and I rotated it, there's certain rotations where you wouldn't be able to tell, right? There's got a threefold rotation, but if I rotated it by 2π/6, right, it would look different. Okay. And similarly, if you translate, well, there's some translations, some discrete translations, which leave it invariant, okay? But, you know, if I translate it by an arbitrary amount, again, it's gonna look different, okay? And so the way that we describe this is that in this case, the spatial symmetries, rotation and translation, have been spontaneously broken as the system cools down, okay? That means that, so spontaneously broken means that the underlying action has the symmetries, okay? So some, you know, you can write down a Lagrangian, or we often like to write down Hamiltonians, okay? But that symmetry is there at the level of the Hamiltonian, the level of the Lagrangian, but the ground state of the system, okay, or the, you know, the state of least free energy at low temperatures breaks that symmetry. And so we say it's spontaneously broken. Okay, so this phenomenon of spontaneous symmetry breaking actually explains a very, very large fraction of the different phases that we see when we look at solid state systems. So here's a couple of examples. You know, maybe you have a material which, as you make it cold, it becomes a ferromagnet, okay? So at high temperatures, so it's got these little magnetic moments. These are, you know, typically you have, you know, atoms where the electrons want to have their spins aligned, and so you have effective large magnetic moments. But, you know, you could think of these as just free spin halves if you want to, okay? And they're sort of, you know, sitting at high temperature. They're, you know, so we depict these spins with little arrows, and each arrow is kind of doing its own thing, okay? It's just, you know, maybe it's fluctuating, okay, quantum fluctuations, or it's, you know, thermal configurations, just picking a random direction in space, okay? And so this picture here has no preferred direction, you know, at high temperatures, and no net magnetization, okay? So if you take this thing and you try to stick it to like your refrigerator, it won't stick because it's not magnetic. Now, if you cool down this magnetic substance, so this is what we mean when we say it's a magnet, okay? We pull it out of the forge, we cool it down, and these spins all want to line up, okay? And when they all line up, they pick a specific direction in space. And now this sample has a net magnetic moment, okay? And now that it has a net magnetic moment, you can measure that direction, right? You can take a bar magnet and actually detect the direction of that magnetic moment. And therefore, this system has spontaneously broken rotational invariance of these spins. Okay. So that's another example. A third example, and the mechanism for this I won't talk about in detail, but many metals, I mean, kind of generically, in fact, things that are metals at high temperature if you cool them down to low temperatures, they become superconductors, okay? And what this means is that suddenly, mysteriously, they start conducting electricity with no resistance, okay? And this is also a sort of spontaneous symmetry breaking transition. And this one, in fact, is very much analogous to the Higgs transition, which is something that I think you guys will probably talk about later in your course, that gives rise to this famous Higgs boson, okay, that was found at the LHC some time ago. And so, just to say that this phenomenon of spontaneous symmetry breaking is realized very, very widely in lots and lots of solid state systems. And, indeed, a lot of us refer to the Higgs mechanism as the Anderson-Higgs mechanism because Phil Anderson described it, roughly at the same time. And he was actually thinking about this phenomenon of superconductivity, okay? And the underlying mechanism is, you can imagine, here's a potential. It has rotational symmetry, okay? But it just so happens that the minimum of that potential, okay, so this, system is trying to find its ground state, and the minimum of that potential is not at this symmetric point 0, but, there's sort of a whole family of different minima, okay, that are related by symmetry. But when the system sort of gets cold and goes into this family of minima, it's going to pick a particular direction, and it's going to break that rotational invariant, okay, that rotational invariance. And so, like I said, this is kind of a nice example because, it took many decades, and again, many billions of dollars, or however hundreds of millions of dollars, to find the Higgs bosons. Whereas, superconductivity is something, and, these things like magnetic order and stuff are things that we can realize in tabletop experiments in a wide array of systems. Okay, so that's one example of how, solid state systems realize classic field theory phenomena, but in a much more experimentally accessible way. And okay. And the other thing is, so we actually use this, sort of field theory describing spontaneous symmetry breaking all the time to understand what a given material is going to do. So here's a sort of example of these are sort of spins, and the spins are sitting on the, on a triangular lattice. So at the corners of triangles, you have a kind of an array of triangles in space, okay? And this is an example of the phase diagram of this system as a function of temperature and some applied magnetic field, right? And using field theory, okay, you can, basically ask, well, what are the, what's the effective potential like this? Okay, it can be more complicated, and what happens to the system as you tune these parameters? What happens to that potential, and also what happens to, the actual sort of state of the system? Because of course, as the temperature goes up, you have more, say, thermal fluctuations, which will eventually destroy this order. So all of that kind of analysis can be done using techniques that you will learn in this course. Okay. Okay. So that's one classic example, spontaneous symmetry breaking. Now I want to talk, and like I said, I'm going to go through this very quickly, but a second, I think, really important class of examples are, you can talk about quantum field theories that you would not think about in the context of, say, high energy physics, but that are nevertheless interesting in their own right to analyze. And I think the most well-known example of this, and a great example of this, is when you try to study a metal and you want to understand what's going to happen to this metal as I cool it down. So a really important difference between metals and the kind of fermions that you are studying in your course, okay, which are typically Dirac fermions, is that, so a Dirac fermion has a single kind of zero energy point, right? Whereas in a metal, we typically have something called a Fermi surface. Okay, so this is a picture. So this is a plot of momentum in the y direction and momentum in the x direction. Okay, and these surfaces depict the points in momentum space where there are zero energy fermions. Okay, so there's this sort of complicated surface where we have fermions at zero energy, and and I'll just come back to this question in a minute. Right, so we have this whole surface instead of just a single point. So I had a question in the chat, and maybe I will pause to answer that. So the question is, spontaneous symmetry breaking is more general than Ginzburg-Landau theory. And so maybe I can, maybe can you say a little bit more about what you mean by more general? Maybe you should type it in the chat because I can't hear. Okay, here we go. Okay, so so I think there's many ways that I could answer this question. So, you know, spontaneous. So Landau-Ginzburg theory is typically, you know, you can apply it in many contexts. So you can write down. So Landau-Ginzburg theory is basically how we take, you know, a system like this, for example, and we write down an effective action that allows us to kind of find the effective potential here. Okay. So now you may have seen Landau-Ginzburg theory specifically in the context of superconductivity, which is, you know, where like it was sort of first introduced, but there's a sense in which this kind of Landau-Ginzburg type theory can also describe these spontaneous symmetry, you know, breaking transitions with magnetic order. There's, you know, all kinds of orders, pneumatic order. Okay, so you know, pretty much any kind of ordering transition you can think of as being described by a Landau-Ginzburg theory. Oh, okay. And so the question, okay. So, okay. And so, yeah, so sorry, different question. So, right. And so in some sense, I would say, you know, Landau-Ginzburg theory is very, you know, is relatively generic, you know, at least when we're not talking about these crystallization transitions. So describing order in a crystal, we wouldn't sort of these spatial distortions. You wouldn't necessarily typically use that, but I sort of think as a tool, it's relatively generic. And the one difference is that, you know, if you're talking about a magnetic transition, right? This is a global symmetry. Spin rotation invariance is a global symmetry. Whereas when we talk about, say, a superconducting transition, so actually here, the symmetry that's being broken, and the reason that this is analogous to the Higgs mechanism is in some sense, you know, the symmetry that's being quote unquote spontaneously broken is the gauge symmetry, you know, associated with electromagnetic charge conservation. And of course, a gauge symmetry is never actually broken, which is why, you know, we should call this the Higgs mechanism or Anderson-Higgs mechanism rather than spontaneous symmetry breaking, but it has this same kind of, you know, picture of an effective potential. So I hope that that addresses the first question. I have another question, which is about basically, are there Goldstone bosons in condensed matter? So absolutely, when we spontaneously break a global symmetry, so this is sort of, you know, something you learn when you study spontaneous symmetry breaking, there are Goldstone bosons. And if we look at this picture, we can sort of understand, just thinking classically, okay, so ignoring quantum fluctuations for now, we can understand what those are, right? There's sort of this minimum of the potential well, and there's a direction where obviously oscillations cost energy, okay? If you want to jiggle around in this direction, you know, and go up and down the hill, that's going to cost energy. And so these, you know, kind of modes associated with your field jiggling this way gapped. On the other hand, this potential has a flat direction, right? And so if you take, very long wavelength distortions that sort of slowly move you around this flat direction, those are gapless, and these are called Goldstone bosons. And yes, absolutely, Goldstone bosons exist in solid state systems. So a nice example is if we take this ferromagnetic picture, okay? There's a mode where all of these spins could just kind of move slowly together, like at very long wavelength in the system. Sorry, not slowly is probably the wrong word, right? So that, the spin sort of as I go along in space, it's going to have this wave. It's going to tip very, very slowly, very long wavelength oscillation. And that is the Goldstone boson, and we also call them spin waves. So absolutely, Goldstone bosons do occur in the context of condensed matter systems. Hopefully that answers the questions. I'll wait for a minute in case anyone has anything else they want to ask about. Okay. Perfect. So, oh, one more. Okay, and then there's a question which asks, are those Goldstone bosons related to skyrmions? And so no, a skyrmion is a sort of a spin texture, a topological defect, which can occur for other energetic reasons. So they're not the same thing. A Goldstone boson is a kind of a wave of spins waving, whereas a skyrmion is a sort of background, like they have some spins are kind of looping around a particular point in space, roughly speaking.
I didn't get that. Could you try again?
Okay. Siri doesn't follow, but that's okay. All right. Okay. And so another, important example of, kinds of quantum field theories now that you wouldn't think about in accelerators are the field theories that we use to understand metals. So you might ask, what's going to happen to this metal when I cool it down? And here you have a complicated set of zero energy states for your fermions called a Fermi surface. And these arrows are showing the different kinds of scattering processes that can happen to these fermions. Okay, so we add some kind of 4-particle interaction, which you can think of as a kind of low energy effective description of the Coulomb interaction in the metal. Okay, and there's all these sort of different scattering processes that are compatible with the requirements of energy and momentum conservation. Okay. And so there's a whole, kind of variation on the kind of field theory you do in electrodynamics, where you ask, what do these interactions do to this Fermi surface? Okay. And so I don't have time to talk very much about it, but this kind of field theoretic analysis of systems with Fermi surfaces allow us to predict what's going to happen, particularly to metals as they cool down. And there are, this is a fantastic tool. There's a very wide range of solid state systems that do all kinds of different things, okay, because they have different Fermi surfaces and different kinds of interactions and so on. And different strengths of interactions. And so you can get all kinds of different orders like superconductivity, magnetism, crystal distortions, and all kinds of fun stuff. Okay. And okay, so I have another question, which is spontaneous symmetry breaking also responsible for any kind of physical changes that are seen in the case of solid clusters in between their ground state and transition state? So, can you clarify what you mean by solid clusters? Like are you thinking of a first order phase transition maybe? Where you have sort of phase separation? So I'm going to maybe go with the assumption that that is what the question is about. So in some phase transitions, right? So, if you look at how water, how ice melts, you can have ice cubes in your glass of water. You can have this kind of coexistence of water and ice at, when you get to 0 degrees Celsius. And so I don't have, too much to say about that specific scenario. But basically, when this spontaneous symmetry breaking happens, the system does go through a phase transition, and there's different kinds of phase transitions. And that, sort of, you can understand that also by thinking about an effective field theory for the system. But when the transitions are first order, you actually get, that basically means that you get a region where these, lumps of symmetry broken stuff, of ordered stuff, can coexist with lumps of stuff where there's no order. So I think the answer to this question is yes. Okay, great. Okay, so one more sort of example of, so, we've seen sort of a classic example of, field application of field theory to solid state, spontaneous symmetry breaking. We've seen, a brief discussion of how new kinds of field theories are used and are motivated by condensed matter and are very useful, again, for understanding phase diagrams of materials. And my third example concerns a kind of field theory which people had actually thought about in the context of mathematics and high energy physics, but which isn't known to have a direct realization in sort of high energy, but absolutely has a direct realization in solid state systems. And so this is a particular kind of topological quantum field theory. I'll say a bit more about what that means in a minute, called Chern-Simons theory. And so the solid state system that realizes this is called the quantum Hall effect. This was the source of many Nobel Prizes in the 1980s. And basically, what the quantum Hall effect is as follows. So around this time, people started to be able to grow sort of semiconductor sandwiches, okay? And the way they do that is not so important, but what they were able to do is effectively, by putting different materials on top of each other, they could isolate a two-dimensional puddle, if you like, of electrons, okay? So, basically, there are, in the original implementation, there was, kind of essentially a semiconductor or insulator here, something that's, basically think of it as an insulator up here. And then there's just a whole bunch of electrons and they're confined to move in two dimensions. Nowadays, people are actually very good at making, genuine two-dimensional materials, such as graphene, for example. And so, now we can really have a, look at electrons in a 2D material. But the basic point is that we have some system where the electron motion is confined to two dimensions. Okay. And so, people started sticking these systems in large magnetic fields and measuring the transport response. Okay, so B here indicates that there's a magnetic field and it's perpendicular to the plane of the sample. And what this plot is showing is measurements of the current, both parallel to the electric field, okay, which is parameterized by, so sigma is a conductivity tensor, and this is parameterized by sigma YY, okay? And also the conductivity perpendicular to the magnetic field, which is parameterized by sigma XY, okay? And so this trace here with these big wiggles and these sort of plateaus that fall to zero, this is the flow of current parallel to the magnetic field. And so what you see is that, there's these regions where this current parallel to the electric field, parallel to the electric field, falls to zero. So this thing kind of looks like an insulator, but the current perpendicular to the electric field is quantized, okay? And so this, because, and you can see that, okay, so this is, the resistivity, so it's like the inverse tensor of this guy measured in particular units, but you can see that these plateaus, it's quantized, meaning that over this broad plateau, it takes on the value of exactly 1 in the right units, okay? And there's other plateau at different values, for example, 3, okay, in these units. Okay, so this is called the quantum Hall effect. And so I'll talk a little bit more about this current flow a little later on, but there is a really kind of interesting observation, which is that this quantization, so this, as I said, is the resistivity, okay? But if you look at the conductivity, it's quantized either in integers, like this plateau here, 1, 2, 3, 4, but it can also, you also see plateaus at certain fractions, notably at 1/3, okay? And, you know, I should say that so these, you know, occur at different values of the magnetic field. So basically, as you get larger flux densities, you can change, you know, what plateau you're at. Okay. Okay, so how does sort of Chern-Simons theory enter into this? And so there's two ways to think about this. You can ask me afterwards. You can actually sort of see that these resistance properties can come out of a sort of effective Chern-Simons action, but let me give you the more exciting picture, okay? And so what's happening at these fractional plateaus in this system? So this was sort of an observation initially made by Bob Laughlin. So he said, you know, let's try and understand this fluid of electrons at this 1/3 plateau. And he said, in order to do this, consider, you know, you're going to take your magnetic field is basically fixed, but you're going to insert one extra flux quantum perpendicular to your sample, okay? Now, when you change the magnetic flux to put this flux quantum in, that is going to generate an electromotive force, right? So this is just kind of basic electrodynamics. And so there's going to be an electric field, you know, kind of going around this way effectively. And normally this would cause a current that's going around this way, okay, as the field comes. And that would, you know, sort of effectively screen that would give you sort of diamagnetism or paramagnetism. But in this case, the current actually flows perpendicular to the field, okay? So some amount of charge is going to be sucked in or pushed out, okay? But let's say it's sucked in towards this flux quantum, okay? And the amount of current that flows, right, is just given by this sigma xy ex, okay? And so you can ask how much charge has come, you know, onto this little point after I insert a single flux quantum. And it turns out that if this Hall conductivity sigma xy is quantized in an integer multiple of E²/h, then inserting this flux quantum brings a charge E, okay? But if it's quantized in a fractional multiple of E²/h, such as 1/3, then it actually brings a charge of E/3, okay? And so Laughlin's sort of observation was that, you know, if you kind of think of what this quantum fluid is, you see that it should have these excitations, which, you know, basically you can think of as a single quantum of magnetic flux with a bound charge of 1/3, okay? So, you know, these excitations in particular have fractional electric charge. It's obviously very different from the fractional electric charge of like a quark, right? Because this is coming from electrons. There's no microscopic particle that has a third charge that, you know, is free in any sense in this system. Okay. So that's cool. Fractional charge is already pretty cool. Oh, and now let's see. Let's see if we can see, there's an animation on this slide. I'm not sure if we can, look at that. Okay. So the other thing that's interesting about this fractional charge, okay, is that you can ask what happens if you then take one of these particles and bring it all the way around the other, okay? And you can think of this process of taking one particle and bringing it all the way around the other. And let me see if I can play this animation again. Here it goes, okay? That's basically the same thing as taking these two particles, they're identical, and exchanging them twice, okay? And so if you did that, okay, so now this is not moving forward for some reason. So if you did that with bosons or fermions, a double exchange would always get you a phase factor of +1, right? Because for fermions, you get -1, but you do it twice, you get +1, and for bosons, you get +1 squared. Okay. On the other hand, okay, so a simple sort of quantum mechanics calculation that you may or may not have seen is when you take a charged particle and you bring it around a magnetic flux, the wave function acquires a phase. Okay, there's just a phase factor that occurs, and that phase basically the phase depends on the charge of the particle in units of E times the magnetic flux enclosed in units of phi naught, the flux quantum. Okay, and so what you find when you do this for fractional quantum Hall particles is that you get this phase factor if the sigma x y is a third E squared over H, you get this phase factor, okay, which is like 2 pi over 3, but more generally you get a phase factor that's not plus or minus 1. Sorry, that's not +1, okay? So these particles we can think of as having self-statistics, statistics that are neither fermionic nor bosonic. So effectively, what has happened in these quantum Hall systems is, we've created some new kind of particle, and it has these exotic exchange statistics. Okay, and an important thing about these statistics, and I'm not going to kind of derive this for you, but basically, these statistics are completely insensitive to the geometrical details. So I could distort my circular path. Let's see if I can play this for you guys. Oh, it doesn't play. I see. It doesn't play for you. Sorry. So I could distort this circular path so that this particle goes around in some, crazy wiggly fashion. Doesn't matter. The net phase factor only depends on the fact that this particle has gone all the way around the other one, and it's still 2 pi over 3. Okay. And so, how do you describe these fractional statistics? Well, there is an effective field theory description that captures them very well, and it's called Chern-Simons theory. Okay, and as I said, Chern-Simons theory, you can also, kind of think of it as an effective theory that gives you the right conductivity. I won't go through the derivation today, but ask me about it if you're curious. So this is an example of what we call a topological quantum field theory. So here's the action, okay? And, the basic intuitive reason that this is topological is that instead of using a metric tensor to contract the indices on these fields, A is a U1 gauge field here, okay? You're using the completely anti-symmetric tensor, okay? So there's no dependence in this Lagrangian on the metric of your of your space-time, and indeed this field theory basically is a top, it gives you, if the partition functions that you calculate with this field theory basically give you sort of topological invariance of the space-time. Okay, so this Chern-Simons, and one of the kinds of topological invariance that you can realize is if you introduce sources, okay, describing these charged particles, okay, you can show that, different world lines of different sources, if you kind of bring one around the other and get this, sort of link in the world lines, that there are indeed statistical phases associated with that. Okay, so Chern-Simons theory is an example, of a theory that was thought about in other contexts. It was actually, originally sort of framed in this way by two mathematicians, Chern and Simons. So they were thinking about topological, kind of invariance. Simons, by the way, this is the same Simons who Simons of the Simons Foundation. Okay, so he later went on to run a hedge fund and earn lots of money, and now he is giving much of that money back to support research at the interface between mathematics and physics. So same person. But I think this is a very nice illustration of how some of these seemingly quite exotic theories, field theories, quantum field theories, can be realized, again, in solid state systems in the lab. Okay. And so So these are just a few examples of some of the fun quantum field theories that are relevant to understanding condensed matter systems. There are many more, okay? And so, this issue of topological quantum field theories is one that occurs in many different contexts. I might talk a little bit about this later, although we probably won't do much with the field theories themselves. If you're interested in Dirac fermions, Majorana fermions, Weyl fermions, okay, these are all, objects that we can realize in solid state systems. Lots of applications for quantum field theories that are not relativistic in interesting ways. Okay, so the Fermi surface is one of a few that you could think about, and so on. Okay, and so yeah, so this is probably a good point to pause, and then okay. And so the topic that I wanted to talk a little bit more about is what we call anomalies and the role that they play in condensed matter physics. And so, basically what I want to talk about is, first I'm going to talk about what is an anomaly, and I'll give you a couple of different pictures. And then I'll give you some examples of, when we find these anomalies essentially in real materials and what we learn from that. And if we have time at the end, although we may not, I can talk a little bit about what studying materials can teach us about anomalies in quantum field theory. And so now I actually am going to switch to the iPad. Oh, hang on. So now am I able to, oh, okay. So I wanted to, can you make my iPad the co-host? Sorry, we should have checked this.
What is the name?
It's just called iPad.
Because I was checking for other device with your name, but
all right. So I wanted to start by giving you a very basic, kind of overview of what is an anomaly in the way that you will, probably see it at the point in a QFT course. Okay. And so, I'm going to talk about that by means of an example, and we'll talk about this example in the solid state context later on, which is called the axial anomaly. Okay. Okay. And so the axial anomaly is as follows. Let's consider just a free Dirac fermion. Okay. And I'm going to think about this being in 1+1 dimensions or 3+1 dimensions. So if it's in 1+1 dimensions, right? Sorry, I should move this over here. So in 1+1 dimensions, what do I mean? Well, gamma 0 is, maybe it's sigma z, okay, 2x2 Pauli matrix in one spatial dimension. The Dirac spinner is, has two components, okay. And then gamma 1, well, maybe that's sigma x, okay. And there's an extra Pauli matrix that anti-commutes with both of these, which we'll call gamma 5, right? And that is, of course, sigma y. Okay. Now there's a similar structure in 2+1D. The Dirac spinner is again a two-component thing, but now I have to use all three Pauli matrices in my Dirac equation. But if I go to 3+1D, then the Dirac spinner is a four-component thing. Okay. And so then we have the usual, gamma matrices, gamma 1, gamma 2, gamma 3, right? So these are the usual ones that go into my equation. And there's another matrix again left over, which is like the product of all of these guys, okay? Maybe with a factor of I, and that's called gamma 5, okay? And so why do I care about this leftover Pauli matrices? Well, let's look at the symmetries of this action. First of all, I can take my fermionic field and I can rotate it by a phase, right? So this is a global, at this point, global U1 symmetry. But of course, this is the same U1 symmetry that, we usually think of as gauged and associated with the electromagnetic field. So we will gauge it in real life, we want to gauge this, right? And it's associated with the electromagnetic gauge symmetry. Okay, so you can check that, obviously this transformation leaves the action invariant, right? Because psi bar, right, has a psi dagger in it, psi dagger gamma 0. And so it gets a minus sign, and so these two cancel out. But there's another symmetry. And that, sorry. And I should say, so you guys have probably seen a little bit about the relationship between symmetries and conserved currents. And so this symmetry has an associated conserved current, which you can find using, kind of Noether's technique, okay, which is just psi bar gamma mu psi. Okay, and this is the electromagnetic current. Now, there's another symmetry under which I rotate the phase of this field by alpha, but now I'm going to put this gamma 5 matrix. Doesn't matter if I'm in one dimension or 3 dimensions, but this gamma 5 matrix up here. Okay, so now this is, phase rotation by a matrix. And when I do this, okay, remember that gamma 5, gamma 0 is minus, gamma 0 is minus gamma 0, gamma 5. Okay, these guys anti-commute. And so when you ask what happens to psi bar, basically this goes to psi bar e to the, again with a plus sign, alpha gamma 5. Okay, and the associated current, I'm just going to call it J twiddle mu, okay, is I psi bar gamma mu gamma 5 psi. Okay. And so, classically, I have these two conserved currents because I have these two symmetries of my Lagrangian. And so what is the anomaly? Okay. And this is, okay, we call it a mixed anomaly. It basically says, if I gauge the U1 electromagnetic symmetry, and what I mean by this, as we'll see in a minute, is that I allow background electromagnetic fields. Okay, i.e. F mu nu is not going to be 0. Okay, then in the quantum theory, okay, this axial current is not conserved. Okay, so classically, right, these guys are both conserved, right? So we have, whoopsie-daisy, we have d mu j mu equals 0, right? And d mu j twiddle mu equals 0 from our classical action. Okay. Okay. And so this is the anomaly. Now, you will probably see some version of the kind of heavy lifting, if you like, of the calculations that can show this using the Dirac equation in a later course. So there's many ways to show this. And but one that's particularly nice, okay, is what's called the Fuji, and I'm not going to do them today because I think you will see them later, but there's something called the Fujikawa method, where you look at the path integral. And you find that in the path integral, there's a measure, right? So we have, sort of integral d psi bar d psi e to the I s, okay, the action. And we find that this guy, so you can say what's going wrong in the quantum theory, okay, and you can actually calculate, and it's a complicated calculation, you can calculate what happens to this determinant when you do this axial rotation, and you find that this is not invariant, okay, under the axial symmetry. Okay. And so you can also do this using diagrammatic calculations. And again, I won't go into the details, but the basic feature of both of these is that, sort of very high energy sort of fluctuations in the quantum field theory are responsible for breaking the axial symmetry. Okay, you can do these calculations and you obtain a very particular response, which in 1 + 1 dimensions looks like d mu. The axial current is E over pi epsilon mu lambda f mu lambda. Okay. All right. So this is the axial anomaly, and now let me, okay. So I'm going to stop sharing this. So that's the axial anomaly, kind of as you will probably see it in, later in your course. Okay. So, okay. I want to tell you a little bit about what this particular anomaly looks like in condensed matter. And actually, maybe in the interest of time, I will skip these slides. I have a couple of slides. This is sort of agnostic of whether you're on the lattice or in the continuum, but I have a couple of slides just saying, if you express your fermions in terms of bosons, which you can do, but I won't have time to go through the details. There's actually a very simple picture of how this anomaly happens. So another way of saying this is I can just take a scalar boson theory. It has two, it actually has two conserved currents as well. One of them is conserved by the equality of mixed partial derivatives. That's what we associate with the electromagnetic current. The other is conserved due to the equations of motion, okay? And when you now add a source for the electromagnetic field, you can see that, so I've set E to 1 here, okay, but you can see that we get this, this non-conservation of the axial current. Okay. So, all right, so you see this, you'll see this in quantum field theory. It's a rather involved calculation involving these loop diagrams and like very high, stuff happening from very high energy modes. And it seems really quite mysterious, okay? So let me tell you where this crops, how to think about this from the condensed matter perspective. Okay, so, and there's a very important thing, which is when we study solid state systems, okay, if you work on a lattice, momentum is effectively periodic. And that's because if your wave function is only defined at discrete points in space, okay, then, say integers, x can only be 0, 1, 2, 3, and so on, then changing your momentum by 2 pi does, nothing to the phase of the wave function, right? It changes the phase of the wave function by 2 pi, e to the I kx changes by 2 pi, and that's undetectable. Okay, so momentum is periodic, and one of the things that means is that so this is a sort of low energy picture of the kind of energy momentum relation you would get on a lattice in a one-dimensional system. Okay, so if I completed this, it has to be periodic, and so it's sort of arc over, and this was just too hard for my PowerPoint drawing skills, but it would arc over like this and arc over like this, and then this would be what we call a Brillouin zone, and the momentum would be periodic. Okay, and so now you can ask, when you look at your Dirac equation, right, we have, what are these, sort of, why is it a two-component spinner? Well, you have a right-moving branch of particles and a left-moving branch of particles. And in a Dirac equation, these would, both these lines would be crossing, and they would be crossing at zero momentum. That would be the Dirac equation. In a one-dimensional material, it's much more typical that you have your right movers at some, crossing the Fermi level. Okay, so this is sort of your Fermi energy at some positive momentum here, and the left movers crossing at some negative momentum here. Okay. And so, what are these two symmetries? Well, the two symmetries are associated with two densities that are classically conserved. Okay, so the total, so first of all, okay, so now I'm gonna, so this, I have this branch here, and this is called right movers, basically because these guys have positive velocity, right? And these I'm gonna call left movers, and these guys have left, negative velocity. Okay, so I'm moving to the left. And then if I don't have background electric fields, classically there are two different conserved densities, which is to say that the total charge is conserved. That's the number of right movers plus the number of left movers. Okay, this is true even if I add interactions, yada yada yada. But also, basically the number of left movers minus the number of right movers minus the number of left movers is also conserved. And this is, basically the density associated with the axial current. Okay, except that now let me just multiply it by the Fermi momentum, so the momentum at which these guys cross the Fermi surface, and now we can associate this axial current with momentum conservation. Okay. Perfect. So how do we understand this funny, mixed anomaly between the, I add a background electric field in one dimension because my UN symmetry is gauged, and suddenly I have this violation of the axial current. Well, what happens when I apply an electric field is that basically I tilt this chemical potential, okay? So that, and what happens, and so this is sort of my cartoon, and this is an image from a paper by Anton Burkov, where he's sort of showing how you would think about this in a continuum version, right? So where I don't know that there's a sort of bottom here. So I turn on these fields, and that's basically going to push the Fermi level down in this left moving branch and up in this right moving branch. And so when I look at the new ground state, I have effectively taken some of these left movers and turned them into right movers. Okay. So this is the condensed matter version of the axial anomaly, and it's just telling us something that is not mysterious at all, which is basically that when we apply an electric field in our, say, one-dimensional system, momentum is not conserved. Okay. All right. And so, and I guess I should pause to ask if there's any questions about this, because we're going to sort of go on from here and talk a little bit more. Okay, so not right now. Okay, perfect. So, so now what I want to do is talk a little bit about, so that's, what I just explained is something that, you take this concept of anomaly, which seems very deep and exotic in the context of a high energy field theory, and we import it into condensed matter, and we get something that, appears very mundane. So that didn't seem very exciting. Let's take this anomaly and do something a little bit more exotic with it. Okay. So what shall we do? Well, let's suppose for a minute that instead of having a theory with both left movers and right movers, I consider a theory with only right movers. Okay. So if you follow the same logic through, if you only have right movers, it turns out that the electromagnetic current is not conserved. And its failure to be conserved is captured by this equation here. Okay. Now, this observation, right? So this is sort of what we call the chiral anomaly for one-dimensional fermions. And, this observation seems pretty terrible, okay? Because again, if you want your electromagnetic symmetry to be gauged, then that tells me that this, you cannot violate a gauge symmetry. It cannot be violated by the measure of the path integral. And so this theory is clearly, very, very troubled and, is physically inconsistent, okay? So it's tempting to say, well, we should just throw these theories in the garbage. They're not going to describe any relevant physical systems. And another argument that you might give for that is that, look, if I'm a solid state person and I'm imagining that, my fermions are actually coming from electrons that, are living in atoms in a lattice, on the lattice, I could just never, on a one-dimensional lattice, I could never generate a dispersion relation like this, right? Because, momentum is periodic. So basically, in order, so this bottom has to join up somehow, right? And so I have to cross the Fermi level a second time. Okay. So you might say that this is completely irrelevant. However, that's not quite true. So it turns out that we do see the chiral anomaly in condensed matter physics, and we see it in particular, we do see chiral fermions, okay, in condensed matter physics, and we see them in particular at the boundaries of these quantum Hall systems. And so I have a question. Okay, and so the question is, if the current fails to be conserved, then should the definition of the energy momentum tensor be more subtle? And so I think you're probably referring to the momentum current failing to be conserved. And so, one thing I will say is that when I say, the momentum is not conserved in this lattice symmetry, in this lattice system, we are not talking about a kind of dynamical metric kind of theory. So, the lattice, we're sort of taking it to be fixed. And so in particular, this is not a symmetry that we can, gauge. And so this is why, you would say, look, you're applying an external electric field, you have to turn that on. That's responsible for putting energy into the system. And so you should think of this as being, so there is energy being dumped into the system from the lab, from this field that you're turning on. And so it's not sort of internally self-contained in terms of that description. So hopefully that answers that question. Okay, cool. All right. So now I want to, so I want to explain to you a little bit about how this works. And so let me, again, I'm going to switch to my iPad. And go. Okay. And so the second thing that I want to sort of write down here is the following. So, okay, so the chiral anomaly and the fractional quantum Hall effect. Okay. So let me start with basically.
Can I do a short comment?
Yes.
I think in the coefficient of the tensor, it should be 0, right? So you can get from there the component of the electromagnetic field. The antisymmetric.
I'm sorry. Yeah. Sorry. This is. I'm sorry. Let me. Yeah. Sorry. You're right. Sorry. You're saying this. Yeah. This should be. So there's really only one non-vanishing component. And here this is the yeah. That's right. So yeah. Sorry. It should be like epsilon mu nu, f mu nu, right? And this is, and I probably want to have a 2 pi. And this is really just the electric field in the x direction. Thank you. Sorry. Thank you. Good. Okay. So let me start with an observation, which is, as I said, in a 1D lattice, right? We basically always have to have right movers and left movers. But suppose that I am in 2 dimensions and I have a boundary. So, and let me, again, this is going to be as a function of kx, and this is the energy, okay? Now, in 2 dimensions, I have kx and ky, okay? And if I kind of make a boundary, then there's no translation invariance in the y direction, so I don't really have ky, but I have just a whole bunch of different energy states, which, sort of think of as being loosely associated with different values of ky. And so I can have, sort of a bunch of bulk states here, okay, and a bunch of bulk states here, okay, as a function of energy. So these would be bulk states. And so when I have these bulk states, and this is actually what, happens in the quantum Hall effect, I can actually have, just sort of a single state living at the boundary that crosses between, these sort of low energy bulk bands and high energy bulk bands. And so this is our sort of chiral mode. Okay. So that's how we reconcile this, we can do all of this on the lattice, we can realize it in a crystal, provided it's at the boundary of the system. Okay, so there's a question about, okay, so someone has, so there's various ways of understanding this anomaly, one of which involves something called the Atiyah-Singer index theorem, which basically, tells you the Atiyah-Singer index theorem, is something about how many sort of fermion modes you have, how this fermion determinant evolves. And so the question is that related to the bulk boundary correspondence? And let me punt a little bit on that. And I'm going to say not in the way that I'm going to describe it. Okay, so, but this is sort of a very basic observation that we can have a band structure, band structure of energy states, okay, on the lattice, where at the boundary of a 2-dimensional system, we can realize a chiral fermion, okay. So now let me just look at this quantum Hall effect bulk theory at nu equals 1, okay. And so as I sort of promised, so this is, sigma x, let's just look at an integer plateau for now, okay. So I'm going to think about this effective action 1 over 4 pi epsilon mu nu lambda a mu d mu a lambda, okay. And you could add a source term here if you wanted to, okay, but this is a good sort of effective action to describe our bulk. It captures when the system is fractional, these interesting statistics. It sort of captures the transverse Hall response. But I won't write down the full theory that does that because we want to add electromagnetic gauge fields. Okay, and so then, but let's just look at this theory, okay? And actually, let me, so these guys are going to be our gauge fields. And let's ask, Okay. Is this invariant? Under, U1 gauge transformations. Okay. And so let's go ahead and do the calculation. Okay. So let's take A mu goes to A mu plus D mu alpha. Alpha is going to be my gauge parameter. Okay. So what happens to L? L goes to L prime, which is 1/4 pi, epsilon mu nu lambda. Okay. And I have this A mu plus D mu alpha. And then I've got a D mu, and then A lambda plus D lambda alpha. Okay. Now, because of this antisymmetric tensor, right, the D nu D lambda alpha part, that's just going to give 0. So what I get is a 1/4 pi epsilon mu nu lambda. And now I have my original part, right, my A mu, D mu A lambda, but I also have this extra part, A D mu alpha, D mu A lambda. Okay. This looks kind of bad. And you might ask, what should we do to get, to get rid of this piece? And the obvious answer is that we should integrate by parts. Okay. So does the action change? Okay. And so the change in the action is 1/4 pi epsilon mu nu lambda. And then we're going to integrate over some 3 manifold. Okay, maybe we won't specify it, right? And then I've got this d mu alpha, d mu A lambda. Okay. So now let's integrate by parts. Right, and so, basically, so basically, if you like, this is the way that we always did in high school. Okay, like dv is like, d mu alpha. Okay, so v is going to be alpha, u is going to be epsilon mu lambda, d mu A lambda, right? And so, I'm going to take du, this is just 0 again by the equality of mixed partial derivatives. So this actually looks good, right? You should be able to integrate by parts, and this is just going to be 0, but there's a catch. And the catch is that there's a boundary term, okay? So we get 0 up to a boundary term. Okay. And so what we find is that the change in the action is just 1/4 pi, and then I have an integral over the boundary of the manifold. And I've got alpha, epsilon mu lambda, f u lambda. Okay, and then I've got some, normal vector. Okay. And so, for example, so let's be a little bit more concrete, right? So let's suppose that the boundary occurs at y = 0. So it's just a fixed value of y, okay, and we allow any x and t. And so now our variation in our action, right, is 1/4 pi, and we're integrating over x and t of, okay, and so now this should be alpha. And I think this, gosh, so I might have lost a factor of 2 here. No, that's good. So alpha ex. Okay. Okay, so moral. Okay. The Chern-Simons action, and this is true in general of many topological actions, is gauge invariant. Okay, it's gauge invariant, up to a boundary. Okay, so something at the boundary. Okay. Okay, and so you might ask, how do we sort of deal with this boundary theory? Okay, so what to do about the boundary? Okay, and let me just first say that the basic picture is that, at the boundary, okay, we in fact will find a chiral fermion. Okay, which is also anomalous. Okay, and we say this chiral fermion sort of cancels the bulk anomaly. Okay. In other words, when you have this bulk Chern-Simons theory, because it is not gauge invariant at the boundary, there has to be, something at the boundary, in the low energy quantum field theory at the boundary that is going to account for that lack of gauge invariance. Now, there's a variety of ways to do this, I particularly like the discussion in David Tong's notes. He has some nice lecture notes. Notes on the quantum Hall effect, okay, where he discusses this way of treating the edge. And so what should we do is we're going to, so the theory is not gauge invariant at the boundary, so we're going to have to just fix a gauge at the boundary of the manifold. Okay, so we cannot allow gauge transformations at the boundary. This is one way around this problem. Okay. And a particularly nice way to fix a gauge is to choose a sort of covariant looking gauge. Okay, we're going to fix A naught minus V AX equal to 0. Okay. And if you like, so you can think of this as just the gauge A naught equals 0 in transformed coordinates. Okay, so I'm just gonna, relativistically invariant action, I can do a coordinate transformation, and I'm gonna let, T prime be T, X prime be X plus VT, Y prime be Y, okay. And in these new coordinates, okay, A naught becomes A naught minus V AX, okay. AX becomes AX, and AY becomes AY, okay. And so this is now just fixing A naught in this new coordinate system is 0. Okay. And okay. And then we're left with, okay, AX prime. So we also, want to sort of not have fields. So we're gonna say, we're not talking about applying background fields to our system. So we're gonna say that A is pure gauge, okay, but we still have AX and AY. Okay, so fixing this equal to 0 is and these being pure gauge, this is enough to get rid of this problem with the gauge variation. Okay. And then when we plug this in, okay, the total action okay, and so we could plug this in anywhere, and we're saying A0 prime is 0 at least at the boundary of M. Okay, so you can take these configurations and you can plug them into the action. Okay, and you find that what you get from this pure gauge configuration is something that's just a boundary term, right? So we'll do this integral at y equals 0 dx prime dt prime of dt phi dx phi. So we've gauge fixed at the boundary, 0, 0 at the boundary, okay? And then we asked what is our effective action if we have like this pure gauge configuration? And we find that it's this boundary term, which has this form, okay, this form here. So now let's write that in our original coordinates. Okay. So if I transform back, this looks like we're going to go back to x and t, right? And this looks like dt phi, dx phi, okay, minus v dx phi all squared. Okay. And so now we can see that actually, so this is one way of seeing that the Chern-Simons theory has the chiral boson at the boundary. So this is our chiral boson. And so how do we see that? Okay. We define, so let's look at a density operator. And I should say that there is a formal way in 1 dimensions only, okay? Well, people have tried to extend it to higher dimensions, but in 1 dimensions, there's a very well-established formal way called bosonization to write fermionic fields in terms of bosonic fields. And when you do that, you find that the fermionic density, right? So this is like J0, okay? And I'll call it rho. And this looks like just dx phi, okay? And so now let's ask, what are the equations of motion of this action? The equations of motion tell us that dt rho minus v dx rho is equal to 0. Okay. And so this tells us that this charge density only moves right? So the solutions to this equation would be of the form, something times e to the I, whatever, some number, t minus, well, 1 over v x. Usually we write it x minus vt, but here we go, okay? So these are particles that only move right. Okay. All right. And so just to sort of recap, okay, we saw that in 1 + 1d, a chiral fermion, or indeed a chiral boson, because we can actually go back and forth between the two using this bosonization mapping, is anomalous. Right, so this electromagnetic current is not conserved, okay? At the same time, when we looked at this 2 + 1d Chern-Simons theory, this is also not gauge invariant. Okay, at the boundary of the system, okay? And so basically the sort of picture And so because it's not gauge invariant, right, there's sort of something, some current non-conservation. And so the picture is basically that in this bulk, there's sort of charge flowing, okay, from the bulk to the boundary. And we say that the anomalies sort of cancel each other out, which basically just means that the consistent way to have this Chern-Simons theory is to have this chiral boson at the boundary. And now so now we just have a few minutes left. And so maybe, okay, and so maybe let me just sort of say a couple of things. So this is what we call a bulk boundary correspondence, okay? And it means the following. So bulk boundary correspondence. Okay. Anomalies in sort of condensed matter systems, are basically often interesting because they often diagnose sort of non-trivial. Okay. And let me just say, this is D+1 dimensions, right? They diagnose non-trivial sort of bulk phases in, D+1, if you like, +1 dimensions. And so there's many other examples. And I think I don't have time to explain them, but maybe I can just say that, for example, you can think about anomalies actually in zero-dimensional quantum field theory, i.e. in quantum mechanics, so anomalies of symmetries, and these diagnose, sort of interesting edge states of 1, so this is 0 + 1, okay, 1 + 1 dimensional systems. And a nice example of this is the Affleck, Kennedy, Lieb, Tashheki, or Haldane spin chain. So I'm just going to write those words down. I don't, I won't sort of go through the details, but this is an example that you may have come across in another course. Other examples include things like topological insulators. Okay. And these occur in sort of 1 + 1, we can have 2 + 1, 3 + 1 dimensional systems. There are real materials that realize these, and also topological superconductors. Okay, and many more. And so let me end there, and take any further questions that you guys have.